A gas grill. When a camping stove that burns gasoline is used, 70% of the energy from the fuel reaches the cooking pot. Okay, so sounds like a 70% efficiency to me, if you know what I'm talking about. The energy density of the gasoline is 35 gigajoules. Wow, that's a lot of energy per meter cubed. And calculate the volume of gasoline needed to raise the temperature of 1 liter of water. So I've got 1 liter from 10 to 100 degrees Celsius. And assume that the heat capacity of the pot is negligible. The specific heat capacity, C, of the water is 4.2 kilojoules per, I just wrote grams, kilojoules per kilogram Kelvin. Okay, now you should already have an idea, given the information that we have, you should already have a pretty good feel for what this question is going to require, right? You have a temperature, you have a specific heat capacity. What can we get with that? Well, you know from Chapter 3, I told you we're going to use everything. We've used some energy stuff. We've used some the conservation in the water problem. Now we've got some thermal stuff. Remember, energy equals mc delta T. All right? So that's what we're going to be able to do. We, knowing how much mass of the water we have, well, it gives us 1 liter of water. Okay, we'll see what we can do with that. 1 liter of water, by the way, is about 1 kilogram. Okay, that's actually how mass and volume are defined, is based off of, well, I mean, there's a better definition for it, but that's how it was initially set up, was that 1 liter of water is 1 kilogram. 1 centimeter cubed is 1 gram. So those relationships would be good to know. I assume that on a exam, if you needed it, they would give this to you. Actually, there was a question previously that gave us the density of water. It was 1,000 kilograms per meter cubed, which is 1 kilogram is 1 liter. So we'll go ahead and use that, which means we know we have 1 kilogram of water. So we'll say the energy that we need is equal to 1 kilogram of water times C, which is 4,200, because it's kilojoules, so I need to turn into joules, so it's an SI, so 4,200, times the change in temperature. We need to go from 10 to 100, so that would be 100 minus 10, and therefore we should be able to punch this into our calculator. So go ahead and punch it in, see what you get. All right, so this is what I got, 378,000 joules, or 3.78 times 10 to the 5th joules. All right, so that's how much energy we need in order to heat up this pot. Okay, now the question is, what is the volume of gasoline needed? Well, we know this is going to turn into an energy conservation. So I'm going to, not energy, a unit conversion. So I'm going to move it up here. I'm starting with 378,000 joules. Okay, most of the time, if it's involving a energy density or specific density or something like that, we are going to be using some type of conversion. Okay, so we need 378,800 joules. Actually, I'm going to do one more thing first before I throw it into my unit conversion thing up there. I am going to use the efficiency because it does say that it's 70% efficient. And so if it's 70% efficient, then that means I need more energy actually coming in, because not all the energy is going to the pot. So if I divide that by 0.7, which is my 70% given, 70% given at the beginning, then I need to get out 540,000 joules, 540,000 joules. Okay, so that's what I'm going to bring up here, 540,000 joules, and then I need to turn that into volume. And I want the joules to cancel out, just like that. And so I'm going to take my energy density, which was 35 gigajoules, so 35 times 10 to the 9th joules per meter cubed. That is the energy density that I was given right here. That will allow the joules to cancel out, and then that will give us a meters cubed. So I'm going to take my number, and I'm going to divide by 35 times 10 to the 9th, and I get a very small number. I get 1.54 times 10 to the, looks like about 10 to the negative 5th meters cubed. So a very small amount of this. That's why you can use, if you've ever used those camping grills, you can use them several times before that small propane tank runs out or gas tank runs out. You can use it for a long, long, long time. All right. So there you go. It's answered the question of the gas grill. All right. Let's move on to another one. There we go. And moving on from the gas grill, we've got now nasty neutrons. How about that? So next question is about nasty neutrons. Almost there. I think we got about 3 more, then we'll be done. I just want to make sure that, like I say, we're getting through all these different types of questions that you might see and getting comfortable with the types of information that you might need from previous units in order to be able to do this. Okay, this one says when a moving neutron strikes a stationary carbon-12 atom head-on, the neutron loses 30% of its kinetic energy. Estimate the number of collisions that would be required for a 1 mega electron volt neutron to be slowed down to 0.1 electron volts. Now, there's a couple of different ways to do this. One way is to say, well, if I start with 1 mega electron volt, that would be 1 million electron volts, and it says every time it hits another carbon, it's going to lose 30%. And so I could say, well, if I lose 30%, that means I still have 70%. So if I lose 0.30, then I have the remainder, which is 0.70. So I could just take that 1 million and multiply by 0.7 and just keep going times 0.7, times 0.7, times 0.7, times 0.7, times 0.7, until I get down to 0.1 electron volts. Okay, that's one way to do it, and you certainly could do that. You could just keep going, equals, 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 enter, 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 and you'd eventually get there. Okay, another way to do it is to recognize, you're going to like this. Well, some of you are going to like this. Some of you are going to be like, oh my goodness, why you bring that into this class? All right, so let's say that our first term is 1 million. Okay, the second term is 1 million times 0.7, or 0.70. Our third term is that times 0.7 again, or in other words, 0.7 squared. Oh, you see where this is going? This is a geometric sequence, which you learned about in your math class. Oh my goodness, your math teacher would be so happy about this. I promise he knows. Anyway, geometric sequence. So you could very easily use this geometric sequence and find the answer. Even if you don't remember your formula, recognize that this variable right here is 1 less than the term, right? That is how many times it's run into another electron. So how many times it needs to run into different electrons. Remember, the first term is actually not important because it hasn't run into an electron yet. Okay, so you could say that I want my power to be 0.1. So this is what I get when I take 1 million and multiply by 0.7 to the x power, and you could do an insolve for x. When you do your insolve for x, it should give you then how many times you need to get. Now, it's probably going to give you a decimal, so always round it up because the collision before won't get you to 0.1. It has to be the next collision, all right? So go ahead, figure that out either by the inner way or by plugging in an insolve and see what you get. I'll tell you what I get. All right, so I got 45.2, which means that it takes 46 collisions. Okay, the 45th collision won't be this low yet. It'll still have too much energy, so it needs the next one so that it actually gets down to 0.1 electron volts. All right, not too bad, right? Just got to use a little bit of math there. All right, anyway, let's move on to the next one. Here we go, Snazzy solar panels. A house requires an average power of 4 kilowatts in order to heat power. The average solar intensity of the at the Earth's surface at the house is 650 watts per meter squared. Calculate the minimum surface area of solar heating panels required to heat the water if the efficiency of the conversion of the panel is 22%. This is fairly normal. This is actually probably a pretty good percentage for a solar panel to get 22%. That's one of the problems with solar panels, is just they just aren't that efficient, unfortunately. But we'll see what we can do here. So we need, this is given to us that we need 4,000 watts, okay, in order to heat our water. Okay, we are getting 650 watts per meter squared from the sun at 22% efficiency. All right. So the first thing we want to do is we want to take care of that efficiency. That tends to be the case, is that if we know how much we're actually getting, we can use that efficiency right away in order to be able to figure out how much we actually get out of it. Okay, so I'm actually going to take my 650 and multiply by that 22%. And I get 143. So we are getting, this is how much we actually get from our solar panels, 143 watts per meter squared. And at this point, it is just a conversion, right? We know that we need 4,000 watts. I know that I want to turn that watts into an area. In order to turn it into an area, then I need to divide by watts, and it tells me right there I get 143 watts for every meter squared. And so then I go 4,000 divided by 143, and I get 4,000 over 143. How about that? No, if I approximate it, I get 27.97. And so my answer, because I'm going to round it at least to 3 digits, is going to be 28 meters squared. Sorry, that shouldn't be a per. Meters squared, because the watts are canceling out. So 28 meters squared. That's how much I need. Now, if you imagine what that is, that's like 7 meters long by about 4 meters tall. That would be both sides of your roof. That's assuming that we do get this 22% efficiency, and that's when we actually get all the sun. If it's cloudy, this is the problem with solar power, is that it's very, very difficult to get all the energy that we need. This is an average size house using average solar intensity. So if you're in the northern part of the world, it's probably not going to work so well. If you're in near the equator, where you get more energy, oh, well, okay, it's very possible that you're going to get more at that point. Okay. So anyway, there you go, 28 meters squared. I think we're ready to move on to the next and last question. Oh, my goober. Let's try one with several steps. Why did I put that one in there? Whew. All right. Here we go. A power plant produces electricity by burning coal using the thermal energy produced as an input to a steam engine, which makes a turbine turn, producing electricity. The plant has a power output of 400 megawatts and operates at an overall efficiency of 35%. Calculate the rate at which thermal energy is being provided by the burning coal. All right. Well, that comes from what we're given here, right? It says the output is 400 megawatts, or 400 million watts, and it has an efficiency of 35%. So if I'm getting that out, then all I need to do is I need to take my 400 megawatts and divide it by 0.35, and that will give me how much energy there was before I lost a whole bunch due to efficiency. So I'm going to go ahead and do that. I'm going to go 400 divided by 0.35 here on my calculator. Beep, 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 beep. And I get 1142.86. Of course, if you're writing this as an answer on an exam, it's perfectly fine to put 1140 because that's rounded to 3 digits. But as long as I'm just kind of working here, I do want to keep all my digits. Even if I am on an exam, I want to keep all my digits if possible, because I'm going to use those later as I go through calculations. So this is the answer to the first part, is that if I want to get 400 megawatts out, I need to be getting 1142.86 megawatts from the coal itself. Okay, so that is the rate at which thermal energy is being provided. The next part is hence. Calculate hence, meaning use the information above. So anytime you see hence, you got to use the information above. If you weren't able to calculate the energy above, then just make something up. It's perfectly fine. You just make something up in that previous question. Don't just throw it into the second equation. In the first question, write down, well, I got 2,000, and then use that number later. And that's perfectly fine. They will give you full credit on the second question, not the first question, because you had no idea how to do the first question. But you can get full credit on that second question. So hence, calculate the rate at which coal is being burned. Note that coal has an energy density of 30 megajoules per kilogram. So how much coal is being burned? Well, we've seen this before. We actually saw this in one of our previous questions. We want to turn that power, that 1142.86 megawatts, into a kilograms. And in order to do that, well, we're going to do this. It does say the rate, so let's go ahead and put this in using our conversions, right? So 1142.86 megawatts. Now what I'm going to do is I'm going to write this megawatts as megajoules per second. The reason being is because I see that the conversion I've got here is in joules, and so if I use joules, it's going to be easier to get things to cancel out later. Okay, so I do want to turn this into kilograms. Okay, I want the megajoules to cancel out. So it does say 30 megajoules for 1 kilogram. And so if I do this and I just divide that previous answer by 30, then I will get my answer. Note that the megajoules cancel out, and I get this number divided by that number, which is 38.1. And the units that I'm left with are kilograms per second. Okay, which is exactly what they're asking for, the rate at which coal is being burned. It's being burned at 38.1 kilograms per second. Okay, so doing the unit conversion and recognizing that all I wanted to do was turn that energy into kilograms ended up giving me the rate. Even though that's kind of a weird question and we don't work with rates super often, usually if you just put it in and you work out to cancel out the units that you need, a lot of the time, that time will just stay in there, right? It'll be there for you, okay? Automatically, it'll be there, all right? So there we go, 38.1 kilograms per second. I've finished part number 2, so this isn't too bad of a multi-step question. It's just using the same ideas that we've used before. And then the thermal energy discarded by the power plant is removed by water. The temperature of the water must not increase more than 5 degrees Celsius. Calculate the rate at which the water must flow. Okay, now it's talking about a temperature change and energy going into the water. That sounds a lot like, and I'm going to do this up here on the right-hand side now. So this sounds a lot like my energy equals MC delta T, right? It does talk about the rate at which the water must flow. So that would be a mass over time. So I'm going to go ahead and go mass over time here. But if I do that divided by time, I got to do this divided by time. Okay, and then I'm going to figure out what to do with that. So it does talk about the thermal energy being discarded by the plant. So which energy is that? Which energy is being discarded by the plant? Well, we're going to assume that's the energy that we don't get out, right? We've said that there's 1142.86 being created, or initially, and we're only getting 400 out. So I'm going to assume then that if I'm producing 1142.86 megawatts and I'm only getting 400 out, that the waste then must be 742.86 megawatts. Okay, so I'm thinking that's probably the amount of energy that's being lost and being put into the water. Okay, from there I can use that inside, because now look at my formula. My formula up here has energy over time, which is power, right? That's what I need, because I do want this to, I forget my finger isn't going to go over to that white screen. I keep trying to point over there. It's not working very well. All right, it's all right. Things like that happen. So I've got this mass over time, which is what I want. I want the rate at which the water has to go by, right? So I need to transfer 742.86 megawatts, which is energy over time, right? Okay, that's going to equal mass over time, which is what I want, times the specific heat of water, which I don't have here, but I was given that in one of the previous questions, right? If you go back to the gas grill, yeah, try grill burning brass. Brass, yeah, that wouldn't work either. Grass, gas grill. 4.2, this is what happens when you create a video that lasts 40 minutes. You start to lose some words. So 4.2 kilojoules. So I'm actually going to get rid of the 0.2 there. We're just going to make this 4,200. That's my specific heat of water, because water is what's heating up, and I want a temperature change of 5, no less. Sorry, no more. It can't be more than 5, because that's a general type of restriction put on industry, is that you can only cause the temperature of the water to change by this much. Otherwise, you're going to seriously affect the wildlife that may be there. Okay, so we get that change. You should be able to then take your 742.86 divided by 4,200 divided by 5. Remember, this one is in megawatts, so that is times 10 to the 6th. Okay, go ahead and calculate it, see what you get, and then I'll show you what I get. All right, and this is what I get. I get 35374.3, which, you know, on an exam, I'd round probably the 3 digits, so I'd probably go 3.54 times 10 to the 1, 2, 3, 4 kilograms per second, and that is the mass flow rate. Now, I know the units is kilograms per second because I used SI on everything else, right? I got megawatts here, which is joules per second. I did turn it into times 10 to the 6 so that it was in watts per watts, and then the 4,200 is the joules per degrees Celsius, which I already per kilogram, which I already took care of, and then the 5 was in Celsius as well, or Kelvin. Change in 5 degrees Celsius is the same thing as change in Kelvin, 5 degrees. Okay, and so my final units in mass per time should be kilograms per second. All right, and that's actually the end of that question. Is we get our, that's a 4 up there, by the way. I know it looks like a 21, but that is definitely a 4. 10 to the 4th kilograms per second, and we know the rate at which the water must flow. That's a lot of water, right? 3.54 times 10 to the 4th kilograms per second. So they're going to have to run a lot of water through there to make sure that they are cooling things off without heating up the water too much and without damaging the environment around them. All right. Okay, that's it. At this point, I think you should be ready to go try some on your own. A lot of them will be very similar to these. Keep in mind the principles, right? Anytime we use that efficiency, we would take care of the efficiency relatively early on. If we knew how much we needed, we could use that efficiency to find out how much must have been going in. If we knew how much was going in, we could use the efficiency to find out how much was going out. Anytime we use specific energy or energy density, that was usually one of these conversion type questions, and so we've used the unit conversion to help cancel things out and get what we wanted. And then we also use the MC delta T, as we saw in this question. We use the energy conservation, the MGH, in the other question. So use those ideas in order to help you answer these questions as you approach them, recognizing that there's not a lot new here. It's just learning how to apply those ideas. All right. Thanks a lot. See you later.